everyone. I'm here to talk to you about Finding Xori, which is a malware analysis triage automated disassembly framework that we designed. And to introduce ourselves, my name is Amanda Rousseau. I'm a malware researcher at Endgame Inc. I look at malware all day, reverse it, write detections for it. Some of you already know me as Malware Unicorn on Twitter, and this is...
Hi, I'm Rich Seymour. I also work at Endgame. I'm a data scientist there, working on bulk processing of malware on our little chatbot Artemis and the Xori thing, which we started in January approximately, about 6 months ago. It's 36,000 lines of code, and we're super excited to tell you about it.
All right. So normally people show you the demo at the end, but how many people actually know what a disassembler is? Woo, okay.
Okay, that's good.
So we'll show you what it is first, and then we'll go into the details. So last minute, like last 2 weeks, we made a UI for it, which my intern helped me with.
This guy.
And so you can just click and drop a file. Let's say wanna cry, right? It will take a few seconds, and it'll disassemble it for you. And you can see this nice little lovely UI. Switch to linear view. Say you wanted to just look at the info. It's pretty basic. It's what we could do in a few weeks. But you kind of get an idea of like what we've been working on. But it's mainly for automated disassembly. So back to the slides. All right. So how it's going to work, I'm going to go over, what's the current state of common disassemblers, like how they handle PE files, as well as the functionality and features, and how we pull together different disassemblers and emulators to get to where we needed to be. And then I showed you a little bit of the demo, but I'll go into some specifics. All right.
Yeah, so the problem is at Endgame, and maybe at all of you at home, you have a ton of malware samples, millions of them, but very few reverse engineers. So the idea with Xori was, is there a way to just bulk process things that may be malware, might be benign, might be pups or whatever, very quickly so you can triage them. And so the idea was, how can we build something scalable and actually useful and most importantly stable?
So we put together this chart. We were kind of looking for a solution for automated disassembly. And so I kind of have these little check boxes and X's as far as evaluating, Capstone, Radari 2, IDA Pro, Hopper, and Binary Ninja, which are pretty common. A lot of people use them. And I found that they have their strengths and weaknesses as far as price. Can it be used for automation? Is it stable? Like for instance, Radari 2 kind of crashes and site faults a lot if you're trying to do specific things. Or, it may have a couple of features that you need or you don't need. So we kind of wanted to lay out the map and see what we could use that's already available. But we found out that we needed these specific requirements.
Yeah, so as I said before, we needed stability. We also needed cross-platform because we're developing on Macs, we're running stuff on Windows, running stuff on Linux, et cetera, et cetera. We wanted output that we could actually read, which if you saw Halvar's talk, I forget where it was, he was talking about this a little bit, like outputting a control flow graph that you could actually read in another tool would be really cool. So that was an important thing for us. Ease of use, depending on if you think disassembly is easy, and then just a core feature set that's on par with some of the other tools that are out there. And then accuracy.
So, the first step was diving into a lot of different open source disassemblers and trying to figure out could I evaluate their accuracy? Could I see what they were doing to make sure that they were performant? How many bugs did they have? What language were they programmed in? How can I integrate it into my language, the languages that we use? So we looked at a lot. So we found that much of Capstone was really nice. It was pretty performant, really fast. As well as it's based off of LLVM and GDB headers, so is more common across Linux distributions. Right. Chemo had some really good emulation that we do some light emulation. I'll get into the features later, and then we took all the things that we liked and developed in Rust. So here's an example of evaluating some of the assembly. So we have x86 32-bit instruction here, which normally hex 66 is the op size, which tells it, do I need to go lower or smaller or bigger? And then the op code, right? So generally 90 means NOP. But in this case, it actually, with object dump, is exchange AX, right? So idapro also does this correctly. But when you look at capstone and like distorm, it's reported as not. So sometimes you want that information to be, correct across all of them, but it's minor changes in specific instructions. All right.
So developing in Rust. How many people here have heard of Rust, the programming language? How many people here have coded up something in Rust? Okay, cool. Camera guy? Excellent. That's great. So Rust has a lot of advantages. It's kind of like that new version of C++. You can't use at work yet because it hasn't been standardized in Microsoft Visual Studio. But it's even better than that. It has a lot of safety features which save you from yourself. Like if you're a terrible programmer like me, it's nice to have your compiler tell you, oh, you forgot the ampersand because you did too many drugs in college to remember how pointers work. And this is more things. You've got stability and speed. It's really fast. That's probably the craziest thing about it. And the other thing is I didn't really know Rust other than just as a fanboy until starting on this. And this was developed really quickly. And I think a lot of that's because this language kept us from falling into a lot of dark holes.
Yeah, it was mainly like, okay, we need to program a project in Rust just to get used to it. And I was like, let's make a disassembler. All right, so current features. Yes, we're open sourcing this, but it's APGL version 3. It currently supports x86 and 64-bit. We do shellcode if it's x86, as well as portable executables. So what does that mean? Down here on the bottom, I simulated the thread and environment block and the process environment block. So if you're doing shellcode and you need to dynamically load any of your Windows APIs, you could do that with a little bit light emulation. You can see it in the output, and I'll show you what I mean by that. It displays strings. So if you're familiar with the Flare libraries where they kind of do emulation to pull out strings from the stack, it does it automatically in the code as it's doing inline. It manages memory. So for instance, if you have the program image versus the stack versus whatever memory you add to it, it will handle it and read safely. So anytime there's an address that is outside of the bounds of what the instructions are doing, it won't do anything. And it outputs JSON, so you can have it in all of your services and automate it. I would like to do message pack, but since JSON was fast, it was doable. So there's two modes. There's light emulation, where it will go through, it'll use a stack to push all the arguments onto the stack when you jump into a function, as well as full emulation, which I don't recommend because I'll need to make it faster. But it works like, say, you're doing packing or you're doing the PEB loading, which I'll explain again. It's pretty slow. But, if you're working with a small program, it'll work. And finally, evaluates functions based off of DLLs, because I have this huge JSON file that has all of the Windows DLLs and all of their offsets and everything. It will populate those, write the actual addresses, and simulate that so that when it accesses a API call, it will actually display it as it was accessed in memory. So design. So we have the PE loader, which basically takes the header information, puts it into the memory image, as well as simulates the TEB and PEB and all the DLLs from the import table. And then we have the manager, which I just explained earlier. And then we have this analysis struct that follows all of the disassembly that's coming out, all the function, builds all the functions, and keeps track of all the imports, as well as the state, which tracks all the registers from the CPU and the flags. It copies like a new state of the stack for when it goes to another function, as well as I introduced loop tracking, and I'll get into a little bit later. It's basically for the emulation part. All right.
Yeah, my thing. We decided to roll our own PE parser mainly because I'd stared at that like Core Kami poster so much that I was like trying to make it real. If you don't know the PE header, it's like a history of DOS, MS-DOS from 8-bit to 16-bit to 32-bit to 64-bit in a little pack of bytes. And so we made this parser that will read through the header and yank out everything out of it. So I tried to get as much obscure stuff in there as possible, not just the stuff you need to load the binary, but also things like what we're looking at here, the DOS stub, like the message it prints out, because sometimes malware analysis like to see like, well, is that corrupted or was it modified or is that a different compiler? So yeah, so it'll read PE32, PE32 plus, and it's pretty stable, pretty good.
All right, so from the output from the PE loader, I'm able to rebuild the image into memory. I put the stack at like a static spot where in the config file you can change that if you wanted to, as well as all the DLLs, like where the DLL address starts, you can configure that, and the TEB and PEB addresses. So if you like want it for a specific environment and you want to have those offsets correct, you can do that, which is nice. And the memory manager handles all of where all of those are and how you access them. All right, and so what I explained before, symbols, so you can make your own symbols. So if you have a bunch of DLLs for like XP or Windows 7 or Windows 10, you can populate those into a nice JSON. It will load them up, recreate the import tables in the PEB and TEB, and you can have it accessible when it's doing the disassembly. So you can customize it for your analysis environment, pretty much. All right. So like I explained, if you're doing shellcode, you're dynamically loading the API calls that you need. So from that, it's simulated to TEB and PEB, and you know I keep saying that, and handle memory management where I segregate everything so that it won't access things that it doesn't need to access. And because functions can be pushed on the stack, you can actually see that as it's happening. And so what do I mean by that? So this is a shellcode routine for loading load library A to be called by the shellcode. But in the actual header imports that the shellcode uses is exit process, get last error, get local time, and get module handle A. But you don't see load library A or shell execute A or virtual protect, right? Because it's going to dynamically load it from the PEB. So you can see, this is the Xori output, by the way. The string will show up like load library A, and that function that it's calling right underneath there is actually getting that address from the stack by comparing the name to the name that's in the PEB. All right, and then once it's done, it moves that address into that pointer 4011 or 1004. And down here is actually where it calls load library A, and you can actually see that in the emulation part of Xori. So it'll nicely populate for you. All right, the thread and process environment block. So I just looked at Wikipedia to get the structs because they're like all out there already. You really don't need the whole like structs from Windows in order to get all the special stuff underneath. I left it in there in case you wanted to use it, but I don't recommend it because it takes a while to load. So basically, the nice thing about Rust is you can serialize structs into bytes. So I was able to recreate the linked list of the PEB and TEB and the PEB loader data, compile that all into a nice serialized bytes, and so the memory manager will handle when the assembly instruction accesses the address to the whatever part, like if it's doing the normal shellcode routine, FS30, go through there. All right. Another thing that we wanted to pay attention to was identifying what's code versus data. And so there's a lot of research papers out there that talk about when to identify padding after a function, junk code after a return. And so we try to do as much as we can by checking off all the boxes of identifying those things and trying to show that in the output. So here's an example of padding after a non-returning call. You can see that this is actually VB5. So right after the call to thir main, I think that's how you say it, is the struct and how it loads all the functions to be called. And you can see if it's a non-returning call, we won't show, we won't try to disassemble it. We'll just show it as data, and it'll try to any function that it links to. It will go and try to disassemble that function if it's in that list. Same with padding after returns. So if you're using like Visual Studio or some other common compiler, it will add a specific type of padding. And you can configure that, but normally it's like CC. So we try to identify that as best as we can. All right, So how do we, another way to identify junk code versus data is that I do this thing called a queue, where if you have a branch statement, if or else, it will follow the jump first, and then the non-jump second. So it'll push all of the jumps to the top of the queue to be analyzed first, and then the left branch will go to the back of the queue. And this is pretty fast, and it'll enumerate, the actual control flow as it goes through very nicely, and it should end properly with all the instructions enumerated, only for the text section so far. All right. So I talked about the loop tracking earlier, and what that is for the light emulation, I found out that sometimes it's possible to get into an infinite loop. So I wanted to configure something that I can't just kill after 4,000 loops or something. So I have that configuration in there because say you just wanted to do quick triage really quick, and you didn't really need to go through those loop cases. Well, I short circuit some of the loops in there. I need some research, but I did best as I can. I would probably put more
the relooper.
Yeah, the relooper algorithm in there to see if that would work better. All right.
Yes, my last week of my life. So for signatures, there are a few signatures built in for standard function headers there, and one nice thing that Rust gives you recently is called byte regex, which is follows people who've used regexes. Now you can use them on bytes, and it pretty much translates. I spent quite a long time importing what are known as flare patterns that were open out there in the world. The problem is all of those depend on IDA Pro internal patterns. So it's like building a tree, but the entire trunk of the tree is in a $3,000 disassembler. So this partially works, but it's definitely the thing that we are looking for the most help with. If you are a master of pattern files or signature files, get in touch with me. But this allows you to add a lot more name info to the things that are compiled into your program.
Yeah. If you wanted to enumerate all of the CRT libraries from Visual Studio, you could do that. There are some open source flirt signatures, but there's different versions for every version of IDA Pro. So unfortunately, the older ones we could do.
Yeah, the real old ones we could do.
All right.
I'm here for the speed. This was crazy, because mostly this was Amanda just doing whatever she does to write a disassembler in 6 months, and me then occasionally running it to see how well it ran. And it runs really, really fast, especially on an SSD. You can do, these were 1,000 samples from Ember, which is a test set that we release the hashes of. If you know how to get the binaries from the hashes, you can download it yourself. This is specifically the one that's in the AI Village and DEF CON. It's just a subset, the test set. And it just guns through these things on an old machine, outputting 5.3 gigabytes of JSON, which then you can do whatever the heck you want. Like if you want to look for all things with crypt, all functions that were called with crypt in the name, just run JQ over all those files, grab it. Or you can take that JSON, throw it into Postgres, Elasticsearch, Mongo, whatever's on the horizon, put it on the blockchain, and and that's it. It's great. It's freaking super fast, super stable.
All right. So simplest way, if you are not familiar with Rust, they have this, once you install it, they have this thing called cargo, just cargo build release. And then as soon as it's done, you can do target release Xori -f, whatever file you want, like WannaCry. If you want to do a basic disassembler, you can. You don't want to actually use the analysis part of it, the disassemblers in there. You could just use it directly on a binary list there, and it'll output without the nice colorful display. If you want to do the file disassembler, you can also access the analysis portion of it. As you can see, this is a simple hello world program in shellcode, and you can see the hello world being popped off of ECX right there. All right, so comparing WannaCry with Xori and IDA Pro, You can see that Adapro has a lot of like cool enumerations for like function arguments, but that's due to like flirt signatures. So we're not there yet, but you know, for 6 months, that's not bad. Same with Radari. Radari has some like similar kind of signature analysis as well for identifying the libraries. But I think the differences between Xori and Radari is that I don't know if Radari actually populates the actual memory addresses of the imports. So it might not show up. Oh, and like I had a GIF ready, but I showed it to you in the beginning. Thanks to my intern for helping me with the UI. All right, and that's pretty much it. It's live now, so you can go download it and play with it off of our GitHub with Endgame Inc. Xori. And if you have any questions, you can like ping us on Twitter or something, or email us directly. We'll give you our email. All right. Thank you.